why can you change one line of code and break something on the other side of the system? Software is deterministic. There's no randomness. Every execution follows exact predictable rules. The computer does exactly what we tell it to do every single time. Yet our systems are deeply unpredictable. This gap between determinism and predictability is the central problem in software design. The problem is causality, specifically, the opacity of causality in our systems. Now, software is a system of causes and effects. An input triggers a transformation that produces an output. A user action causes a database update. That update triggers a notification. Each step is a link in a causal chain. Every function encodes a causal relationship. Every state change is an effect of some cause. The entire system is a graph of causes and effects. Now, here's a critical distinction. There's a difference between execution and reasoning. Execution is what happens when you run the code. The computer follows the instructions and produces a result. Reasoning is what you do before you run the code. You look at a change and predict what will happen. You read a function and understand its behavior. You trace a bug from effect to cause. Good design is design that preserves your ability to reason. Now, when a system has clear causality, you can predict its behavior without executing it. You can see a function and know what it affects. You can make a change and foresee its impact. You can trace a bug backwards without running a debugger through 1,000 steps. This is maintainability. This is the foundation of trust in a system. The quality of a design depends on how transparently these causal relationships can be understood, reasoned about, and maintained. When you can reason about causality, you can modify the system safely, add features with confidence, and find bugs efficiently. When causality becomes opaque, the system becomes a black box. Now, there are four mechanisms that destroy causality. The first is hidden dependencies. Now, assume there's a function called calculate price that takes a product ID and returns a price. Seems simple from a causality perspective, but it also reads global discount registry. That registry is modified by a background job. That job runs on a configuration. The configuration differs between environments. The actual causal chain, product ID, and current time, and background job state, and configuration all combine to produce the price. The function signature promises simple causality. The reality is vastly more complex. Now, this is spooky action at a distance. Effects appear from nowhere, triggered by invisible causes. The second is global state. When anything can modify anything, cause and effect become impossible to trace. A global configuration object that hundreds of functions read and dozens write to. The question is, if I change one value, what breaks? Now, you can't answer that question without reading every function in the system. The causal graph is fully connected. Everything affects everything. Local reasoning becomes impossible. The third is implicit side effects. A function get username takes a user ID and returns a name. Except it also logs the access, updates a cache, sends analytical events, checks permissions, and triggers lazy loads. The signature says I give you a name. The causal reality is I cause 7 different things to happen across the system, one of which produces a name. You can't reason about the code by reading its interface. You must read the implementation and the implementation of everything it calls recursively. And the last one is tangled time. Now, if two functions modify the same data structure, which of them runs first. If they are in different threads, different processes, different services, if one is triggered by a user and another by a scheduled job. Causality now depends not just on what runs, but when. And when is invisible in the code. The causal graph changes with every execution. Now let's look at an example, a bug report, where a shopping cart occasionally shows the wrong total. You go ahead and find the calculate total method. It looks simple. Sum prices, apply discounts, and add tax. But the prices come from a cache updated asynchronously. The discounts are in a global state modified by different multiple services. Tax calculation writes to audit logs and updates analytics. And multiple browser tabs trigger calculations simultaneously. These are all the four, reasons why causality breaks down that we talked about. What looked like simple causality is a rat's nest of hidden causes. To understand why the total is wrong, you need to understand the state of a dozen systems at one precise moment. This is causal opacity. Reasoning becomes impossible. Now, how do we actually think about code? When you read code, you're building a mental model. You're simulating execution in your head. Now, human working memory holds approximately 4 to 7 items at once. This is a fundamental cognitive limit. You can trace maybe 5 causal steps simultaneously. Input to transformation A to transformation B to output. You can reason about this. But when the function depends on hidden global state, you need to hold the function's logic and the state's value and everything that might have modified it. You've exceeded cognitive capacity. Now, when there are implicit side effects, you must track not just the primary causal chain but all secondary chains branching from it. That leads to cognitive overload. When timing matters, you must simulate multiple concurrent paths and their interactions. That's impossible to hold in working memory. And that is why we kind of rely on local reasoning. You understand a piece of code in isolation without understanding the entire system. You look at a function, understand its inputs and output, and know what it does. Local reasoning is only possible when causality is explained and contained. When causality is opaque, local reasoning breaks down. To understand any part, you must understand all of it, or at least far more than you can hold in your head. Now, there's a profound psychological difference between confident and uncertain changes. When you can reason about causality, changes feel safe. You understand the impact. Even if wrong, you understand why. When you can't reason about causality, changes feel dangerous. You modify something and genuinely don't know what will happen. You run the full test suite anxiously. You push to production with dread. This isn't imposter syndrome. This is rational response to causal opacity. Now, studies show that confidence, the subjective feeling that you understand what you're doing, is one of the strongest predictors of developer effectiveness. Causal opacity destroys confidence. Destroyed confidence destroys productivity. When we obscure causality, we work against the fundamental way human minds process information. Now, code bases that slow down over time, early features fly out, months later, everything takes longer. A year in, the team crawls. Almost all tech debt is causal debt, the accumulation of opaque causality. Each hidden dependency, each global state, each implicit side effect adds invisible edges to the causal graph. Now, causal debt compounds. When you can't reason about a system, you make defensive changes. You add workarounds instead of fixes. You duplicate logic instead of refactoring because you are afraid to touch the original. Each defensive change adds more opacity. But the cost isn't just velocity, it's cognitive load. Every developer in a causally opaque system operates under constant cognitive stress. They're holding more in their heads than necessary. They're making decisions without full information. They're guessing constantly. This leads to burnout and turnover. Organizations where the longest tenured developers are most valuable, not because they're better engineers, but because they've memorized the invisible causal graph. When they leave, the knowledge disappears. It's not encoded in the system, it's only there in their head. Think about this for a moment. Then there's fear driven development. When you can't predict consequences, you become afraid to change anything. Innovation stops. The system calcifies. Companies where deploying a simple feature takes months because nobody understands the causality. Where can we add this? Always gets probably, but we need to test everything because we don't know what might break. Technical debt is causal debt. Code quality is causal clarity. Maintainability is the ability to reason about cause and effect. Now, one question: can you understand how actions lead to consequences in the system? If yes, your system is well designed, regardless of technologies or patterns. If no, your system is poorly designed, no matter how elegant. Software is a system of causes and effects. Code serves two audiences: the computer that executes it and the humans who reason about it. The computer needs correctness, humans need transparency. The ability to trace from cause to effect without running a debugger, to predict consequences before making changes. Good design preserves causality, it makes the invisible visible. Now, in the next lecture, we'll talk about that if causal opacity is the disease, what does causal hygiene look like? What principles and patterns preserve the ability to reason? We'll examine architecture through this lens and discover that every enduring design pattern is fundamentally an attempt to clarify and contain causality.